Hi, I'm Dalton.
Hi,
I'm Alan.
and I'm Ryan.
And I'm Nathan, and this is our buck boost converter project.
For our final project, we were to design a buck boost converter with a given input of 12 volts DC and an output voltage range of 9 to 15 volts DC by adjusting the duty cycle. The output ripple voltage had to be less than 2% and the efficiency had to be greater than 60%. We also were to design it as cheaply as possible. Next, Nathan will take us through some calculations on how we went through our design.
The first equation we use to calculate our duty cycle when there's an output of 9 volts and 15 volts. At 9 volts there's a duty cycle of 42.9% and at 15 volts it's 55.6%. We designed the system to be in continuous mode at all times. We chose a frequency of 30 kilohertz to be above the audible range, and we chose an inductive value so that our R max could be around 125 ohms. We also chose the frequency to be 30 kilohertz so that it would allow us to implement an optocoupler if we chose to do so. The optocoupler we were going to use was similar to the one in lab, which had a bandwidth of 30 kilohertz. We found that there is no price difference between a 14.3 microfarad and a 33 microfarad, which is the one that we used, as you'll see in our schematic. To obtain 4.5 watts, we had to have a load of 50 ohms. We would have an average current of 0.3 amps. The ripple results, which are the last equation, will be discussed later. Next, we will be discussing our schematic. In this schematic, you will see the topology of a buck boost converter that was derived in class. There is a 2 amp fuse connected to the output of the 12 volt DC source. This is to protect our system. There is a 100 ohm resistor connected to the output of the gate driver. This is to protect both the gate driver and MOSFET from current spikes upon switching. There's a Schottky diode, which is used in instances like this because there is a lower turn-on voltage and it can change very fast. You can see that we used the inductor, capacitor, and resistor values described earlier. Because this is a low side gate driver, we had to float the ground off of the source of the transistor. This is connected to the function generator, gate driver, and 5 volt DC power supply.
When choosing parts, we kept in mind that we were going to use a frequency of 30 kilohertz, have a max output voltage of 15 volts, and a rough source current of about 400 milliamps. We chose the 13N06L MOSFET to meet the specifications, which allowed us to have a max continuous current of 10 amps, a max voltage of 60 volts, a turn-on voltage of around 2.5 volts, and a minimum bandwidth of 2.82 megahertz. We used a D041 Schottky diode, which is rated for a 1 amp continuous at 20 volts. We then decided on the MIC4428 gate driver that had a bandwidth of 1.73 megahertz. When deciding on the parts, we kept in mind to keep our costs down, and we broke up our overall costs in individual, which is what we actually paid for, and if we were to mass produce these, we said we would produce 1,000. So as you can see, the total cost for us was $8.43, and if we were to mass produce this, it would be around $2.96 per board.
Before ordering parts, we decided to build our schematic in PSpice to verify that we would meet design specifications. Here is shown the basic topology of a buck boost converter with our 680 microhenry inductor, our 33 microfarad capacitor, and our 50 ohm load. Our first simulation, we used a duty cycle of 42.86%. That gave us an output voltage of 9 with an output voltage ripple rate of 0.99%. Our next simulation we ran with a duty cycle of 55.55%. That gave us an output voltage of 15 volts and an output voltage ripple rate of 1.14%. Both simulations illustrated that the design specifications given to us were met.
Alright, next we're going to show you our actual measurements compared to some of the values that we got when we calculated the values out. So first of all, here we're looking at when we used a duty cycle of 42.4, which gave us an output voltage of 9 volts. The output voltage ripple was 80 millivolts, which results in a voltage ripple rate of 0.8%. And for both of these, we used a load resistance of 50.01. Alright, then next we have the actual measurements when we used a duty cycle of 56.7%, which gave us an output voltage of 15 volts. As you can see, we have a voltage ripple of 200 millivolts, which results in a voltage ripple rate of 1.3% with a load resistance of 50.01. As you can see, all these values that we've just found are within our design specifications. Alright, well here's our circuit. As you can see here, here's the MOSFET with the heatsink on it. Here's our gate driver. Here's our inductor with the diode right next to it. And our capacitor is over here. We also included a fuse to make sure that there were no current spikes to destroy our circuit. And right here is our load. We chose a potentiometer so we could change the load if we wanted to. And we are using a 12 volt source and a 6 volt source to power the gate driver.
And we're using a function generator to control the switching of the circuit.
Alright, and here is what the soldering looks like underneath. Pretty good, not perfect, but pretty good.
We set up our circuit so that we could put in a different load other than just a standard resistor. And we had this DC motor from one of Ryan's former projects, so we decided to hook it up and see what we could do. And as you can see, it functions. As we increase the duty cycle, we increase the speed because we're increasing the average voltage across the motor. Nice cool breeze for you. So just to wrap up our presentation, we calculated the power for our load, and at 9 volts we are absorbing 1.62 watts, and at 15 volts 4.49 watts. And to measure the efficiency, we just took the output power and divided by the total input power, and that gave us 77.5% and 80.6% for the 15 volt load.